very good thing that that was addressed. Okay. All right. So deprotonates the phenol. If the conjugate base is relatively stable after the deprotonation happens. Okay? That's what determines the likelihood of a deprotonation happening. All right? Same with leaving groups. Okay? This is only going to behave as an electrophile if the leaving group is relatively stable once it leaves. Okay? And you'll learn, you know, good leaving groups versus bad leaving groups in electric groups. Okay? But if you notice, that's the key bond that we had to make to get our product. Okay? And then in the end, we have got this anion. Potassium is the counter ion. Okay, it used to be the counter ion to the base. Now it's the counter ion to our leaving group. Okay. There was also something in there called tetrabutyl ammonium bromide. And this could have a couple of different roles. I think the most likely role that it has is what's called a phase transfer catalyst. Potassium carbonate is not very soluble in organic solvents. Okay? It's highly charged, so it doesn't tend to be very soluble. However, if you have this floating around, every once in a while, this gigantic, very organic, see all these CH2s and stuff, very organic cation will hook up with carbonate, and they together will go into the organic phase. That's what it's called, a phase transfer catalyst. Okay. All right. At the end of the reaction, you're going to have all this in solution. Okay. So what we're going to do to separate it, we don't want this stuff. Okay. What we're going to do is a liquid-liquid extraction, just like we guys done last week. Salt, these are all salt impurities. Remove with a liquid extraction. Okay. Just like last time, you're going to do it in your culture tube. Okay. Alright. You're going to add a bunch of water at the end. Alright. And dimethyl carbonate will be is soluble in water. Okay. Potassium carbonate. All this is soluble in water. Okay, so we have our aqueous layer, and that's where our salts go. Okay. And then we have our organic layer, then this is our organic compounds. Okay? And that could be product, remains to be seen. Starting material remains to be seen. Unreactive starting material remains to be seen. Other, don't know. But all your organic stuff will go up in there. Okay, and that is our, by the way, 20% ethyl acetate in hexane. Okay, it's a little bit of a strange, you know. A lot of the time we do these with just a straight out of the bottle. Oh, 100% ethyl acetate, or whatever. The 100% ether is a very common one. This one was discovered that we could get rid of the ammonium bromide if we use this one. The ammonium bromide wouldn't go into the organic layer. This is pretty organic soluble, so a lot of organic solvents that we might have used would have had this come along, and then it would have totally fouled up our product mixture. Okay? We want to get rid of all this stuff. Okay? So you're going to do a number of extractions. You're going to, first of all, you're going to get it into the culture tube. Okay? And you're going to get it in there using the 20% ethyl acetate hexane. Okay? And then shake it up, remove the bottom layer. You'll add some more bottom layer so that we make sure we get all of it. Okay? All right, no, I'm sorry. I think you do it the reverse. You remove the top layer. Do it how it's described in there, but do pay attention to whether you remove the top layer or the bottom layer. Okay? At the very end, you'll have a tube that just has organic in it. Okay? And you're going to add saturated sodium chloride to that. All right? We do that because, strangely enough, this organic layer will end up having a little bit of water mixed in it. And if you combine it with sodium chloride water, all that water that's trapped in here goes to that sodium. Okay, so it actually helps, strangely enough, it actually helps dry that organic layer. Okay, but it doesn't dry it enough. So we get that final drying of the organic layer by putting in a little bit of magnesium sulfate. And I always give straight, you know, like I had the thing with the IR nerds. So this is, you know, probably going to be about the size of a chickpea, you know, and I don't know, I would say in there, I think maybe 2 or 3 chickpeas. But you have a visual indicator whether you have got enough magnesium sulfate in there. And I call it snow globe, okay? You put in the couple of chickpeas and magnesium sulfate, you shake it up, and what it's doing is any water that's in there, it's going to clump up, okay? If you got nothing but clumps in there, you haven't added enough, okay? If you add some, and you've got some clump, but you've also got some free-flowing powder, there wouldn't be any free-flowing powder if there was still water left in there. It would clump up with water. So the free-flowing powder is your visual indicator. Oh, I've added enough now. One last thing I wanted to, after you have this, oh, you got your phone now? Oh, there it is. I'm on that real quick. All right. Once you have, you know, you got free-flowing powder, you're confident that it's dry, you need to filter out that free flow, the magnesium sulfate, and get it separated. So what you're going to do is you're going to take, and really, now we're talking about a pea, green pea, of cotton. You stuff it down in there, okay? And then you pour your stuff through there. That'll catch the magnesium sulfate. The organic will go down into your beaker. We're going to put your beakers back in the hood. And we're going to evaporate the 20% hexane ethyl acetate. This stuff won't evaporate particularly well, okay? So we'll get rid of the salt and we'll be left with just how much stuff you have. And then next week we'll analyze to answer these questions. How much product? How much started material? Okay? Any questions, guys? Okay, awesome. Thanks, good.